In this video, I want to discuss what does APY mean and how do you figure out the doubling time? Because there's a few various homework questions that get into this, and I didn't want you guys to have to figure it out all on your own. And you could Google these things, but depending on the source, it can be confusing and can lead you to do the wrong thing, depending on the situation. But let's start with APY. APY stands for annual percentage yield, and it is a value that it's like an associated interest rate for an account. So your account has an APR, which is sometimes called the nominal interest rate. It's kind of like 5%. But as we saw in the past example, when I have a 3% interest rate, that can mean different things depending on the number of times that it's compounded. Um, and that's why we sometimes call it a nominal interest rate. So the annual percentage yield is sometimes called the effective interest rate, which is like, well, how much is it actually growing on a percent basis per year? And like if something's compounded monthly, it will have a different APY than APR. And a lot of times, and basically the point of it is to try to say, okay, what is the net rate of growth in 1 year? That's the yield, the annual percentage yield. And a lot of times, like a credit card statement will give you the APY instead of the APR. And the point of that is to try to cut through the BS, all the financial lingo, and just say, okay, what's your yield instead of what's your growth. But usually it's just a translation from base rate to compounded monthly. In terms of doing that. But basically, if you want to find the APY, there's a lot of different formulas for doing so, but I tried to give you a fairly simple formula to try to use. But what it says to do is to find the APY, you want to take the future value after 1 year and figure out how much it's grown. Because basically, I want to know how much has it grown. And so the formula says take the future value after 1 year, subtract the principal, and then divide it by the principal. So actually, let's throw some numbers into this, and then I'll kind of talk about the sense as we go. So it says, for example, 9, calculate the APY of the CD, and do the same for example 10. So basically, let's say we were compounding monthly or continuously. What were the APY of these accounts? Then they both had an APR of 3%. But in order to do this, we don't want to use this future value. We want to know, well, what was the future value after 1 year? So for example 9, it was growing using monthly compounding. So we want to know what is the future value after 1 year. So let's go ahead and do that first. And that would be, well, we started with $10,000. We 1 plus the interest rate, we had a 3% interest rate, and we were compounding monthly. And then it was over, again, we were compounding monthly, and it was over the course of 4 years. But in this case, we want to know, well, how much was it after 1 year? Because we want to know, well, what was the yearly yield? What was the annual percentage yield? And that would give me that would be based on how much was it at after 1 year. So that's going to be 10,000 times 1 plus 0.03 divided by 12 raised to the 12 power. And basically, I'm figuring out how much is the net growth over 1 year, which was $10,304.16. And if I do that and I subtract the principal, so if I take what it says to do in the packet, which is the APY is equal to that, and subtract the principal. Well, the principal was just how much I started, which was just $10,000, and then I'm supposed to divide by the principal. So essentially, what I'm going to get here is the difference between F minus P, which, remember what I said in that's always going to be the interest. So this would be my annual interest in that situation. And if I divide it by the principal, it's going to give me a percentage. What was the raw growth? Because it grew by $304.16, and that was in the scale of $10,000. And if we go ahead and do that math, 304.16 divided by 10,000, that would leave me with approximately 0.030416, which since that's a decimal, I could convert that to a percentage, would be about 3.04%. But basically, I could come up with what is my APY or what is my effective interest rate? Which is essentially just telling me what's the yearly growth. And it's sort of like converting it from a compounded monthly to just a net growth formula, which is 3.04%. Anyways, but notice, at the end of the day, the difference between APR 3% and APY 3.04% is usually not that extreme. So the difference is not typically that great. But if it's a higher interest rate and it's compounded more frequently, there can be more of a difference. And also as a note, there actually is a much simpler formula for all this if you want to look it up. But the reason I am presenting it this way is just to um, try to make some sense about, okay, well, why is this, what is this number and what does it mean? But notice it's kind of the same mathematical structure as the percent error or the relative error formula, right? It's just like, well, what's the difference? What's the percentage difference compared to the original um, at the end of the day? And let's go ahead and do one last example and wrap up this lecture section. And I'll save example 10 for you to try on your own. But let's say we wanted to figure out what we call the doubling time of an investment, which is basically something that is if you know the interest rate, it does not actually depend on the principal at all. The amount of time it will take for an account to double in value is just specifically dependent on its interest rate and obviously the type of compounding. But if you know the APY, you can kind of cut through the BS and ignore the compounding and just focus on exactly how long it will double based on the percentage yield. So the formula for it is shown below, which is basically a compounded formula, and we set it equal to 2 to know when it will double. And basically to solve this formula, we want to know, well, what exponent will make this happen? How many times do I need to how many periods do you need to put this through for it to double? But solving for t is a little bit tricky, but if I took the natural log of both sides and I divided by the natural log of 1 plus APY, the t would drop out by rules of logarithms. But anyways, due to algebra reasons, which we don't really need to review right now, we could solve for t and that would leave us with this. So really, I should have just given you this formula. And again, if you look it up online, you can find various different formulas for doing exactly the same thing. But this one is coded to use the effective interest rate. So the doubling time is the natural log of 2 divided by the natural log of 1 plus the APY. So in this case, it asks us, well, let's say that our account has an annual percentage yield of 14.87%. We want to know the doubling time. We could just throw it into the formula and come up with our answer. And I know I'm not like going too in depth in this case, and really it's because it's not really that important, and the algebra is involving some logarithms, which is I know that not everybody is super strong in, but anyways, what we end up with is approximately 5 for our value of t, which is the doubling time. Again, that would be in years. So basically, in an account, if I want to know how long it's going to take to double, it's kind of a nice number to know, and it's associated to strictly the interest rate and the type of compounding, or really, if you know the APY, you can determine its doubling time, which gives you kind of a context for its speed. Every 5 years it's going to double. That's pretty fast. Whereas, say for example, I wanted to know what's the doubling time with an APY of 3.04. Oops, I can't type. So in the example number 9, we had an APY of 3.04%. It would have taken 23 years for that account to double, which is obviously an extreme difference. So whereas like if you're looking at just interest rates 3%, 4%, 5%, 10%, they don't necessarily seem all that significant, but minute differences in interest rates can make a pretty extreme impact in especially long-term differences in the type of compounding. So anyways, in the next lecture, we're going to get into amortization formula, which is the math behind loan repayments. And so we're going to kind of start fresh with a new formula and talk about a little bit about that context. But this will wrap up our talks into uh, interest and some very basic finance, because obviously it's very important, and a lot of time we don't really cover these types of concepts in algebra, which it's very important use of mathematics, because finance is something that we all have to live with, even if like some I've been asked by my students, why don't you teach finance or why don't you go do finance? It's just not something that I'm that passionate about. Because I do really enjoy math, but the math behind money to me is a little bit, um, you know, it's a little bit more tedious, and investing is quite interesting, but you know, another thing that I didn't really get into is, well, where does the money come from, right? If I'm investing money, if I'm giving money to a bank and they're giving me back more, why? Like where does this interest, where does it come from? And that's kind of something where you can get into the ethics of it. It just really depends on what's happening. Like if you're investing in the government, a lot of times that money would be going to fund a war or whatever, and when you get back the proceeds of interest, you're kind of profiting on those wartime activities. Or say you're investing in a corporation, you're kind of investing in their startup. If they're making a ton of money from their company, that's kind of the money you're getting back is kind of like a part of that. You're kind of involved in that process. And some companies are worth investing in, and some, the ethics of it depends on, how do you really believe in this company or not, and do you think they're doing something good or not? Because, in if you're trying to apply ethics and a Christian perspective to finance, it's a whole nother thing. And obviously, I'm trying to focus on the math because this is a math class, but it's kind of interesting to think, interesting, no pun intended, to really think about why interest actually works. And like if I'm investing in a bank, why am I getting extra money back? Where it's often coming from someone else who defaulted on a loan or whatever. Anyways, I think understanding the math, to me, it's all about the math, and I really enjoy the mathematical side of it. And while we're not really getting into the deep math concepts like calculus or whatever, it's still important to know, right? And interest is something we're all going to be faced with. We're going to either be borrowing money or investing money at some point in our lives. Just for being a part of society, it's something that you really can't avoid, and so hopefully this has helped with the basics of understanding how interest works. And I think having a starting point, having a formula is nice. And really, that I like to focus on what's actually going on, what math is happening. But anyways, next we'll move on to the next section in the next video.